Hi, I'm Gary, and I want to show you how I use Cloudy. So we've seen ways to characterize the radiation field, its SED shape, and then its brightness. The ionization parameter is a very convenient way for many applications. What I want to do today is set up a very simple sim and vary the ionization parameter and see how the gas changes. So I have here a model that I have already set up, and it is called varyU. Top down, we start with set save prefix. There's two different save commands in the file, so I want to give them both the same first name. So I specify it with the prefix. It's a simple black body, typical of an O star. This is a demonstration of the ionization parameter. So the third line gives it as a log of the ionization parameter, and then it includes the vary keyword because we're going to do a grid over this parameter. The grid command tells it to vary the ionization parameter from 10 to the minus 4 to 10 to the 4 in one dex steps. So that's a huge range in ionization parameter. And one order of magnitude steps is very big. Uh, Modest changes in the ionization parameter change the spectrum in ways that you notice. We have to get cloudy to run. So we'll specify the hydrogen density, just take a number, 10 to the 5. And this is not going to be a full model. I'm going to do a trick with the save overview file. So I'm just going to do one zone, and I'm setting the thickness to be 1 centimeter. So this is going to be the unit cell again. So that we're doing a cubic centimeter of gas. What we're going to do, our trick here is we're going to do the save overview file. And so this saves the temperature ionization at every point in a thick cloud. We used it for the M16 homework. The trick here is we're just going to do one zone that we're going to do save overview, but we're going to loop over different ionization parameters. And so we'll have a look at the overview file. It's going to have all the results in the save overview, but it's going to be only one line per model. There's only one zone, and then they're going to be sequential with increasing ionization parameter. It's very convenient to make plots. We need the grid points for two reasons. One, we need the values of each model that we have generated. So this will give the ionization parameter, but also it gives a summary of the exit details, whether there are any problems. So let's quit here, and then let's run the model. Done. Let's see how things went. Let's look at the grid points. So the first thing we look at is the columns of Fs. So that's the answer. Were there any failures? Were there any warnings? They're all false. So that's okay. And then we look at the exit code. They're all okay. So the models all ran. And then number we're going to need here is the ionization parameters. This screen, the second to last column, is a log of the ionization parameter. So let's exit that. And then just to see what's over here, here is the overview file. Let's go to the beginning of it. So the first column is the depth. That's always the same. This is the temperature. So these are the temperatures of the different models. We'll make a plot of it in a second as we increase the ionization parameter. So we see the temperature change by a factor of 2, although we change the radiation to gas light by 8 orders of magnitude. It only changes temperature by 2. And we see the other quantities change. But we'll come back and we'll look at plots of that. So with that, let's go on over to views. And I've started making some plots. The first, so I do is I do data enter, bring in the grid foot points. And I give it a name that includes GRD for grid underscore, and then you can find the grid columns with that. And then I've brought in the overview file. So I'm going to make the first XY plot, and you select what you want. So I go to the grid file and check out the ionization parameter. And then for the Y data, I'm taking the temperature. The next thing I've done, I put labels on the axis. The next thing I've done is I've used a spline to interpolate, because we have some very wide steps here. So you see, it's not a monotonic function of the ionization parameter. It's complex at low temperatures. That's very typical of the ISM because there's more than one phase possible. And so this it goes up, more or less a monotonic after the rise really gets going and the temperature goes up. Let's look at how the ionization is changing as the temperature changes. So the temperature is a derived quantity from energy equilibrium. This is what cloudy does. Also does the ionization structure, the ionization degree. So on this one, what I've done is use the different columns from the overview file shown here and picked out for the x-axis, again, the ionization parameter, but for the y-axis, the tabulated ionization fractions of hydrogen. So this is the fraction of hydrogen is atomic. That's the first one. So here's the atomic fraction. The fraction of atomic, the next column over in that file is the O plus abundance. So this is the fraction of oxygen, the singly ionized. So you see this reaches a peak at about an ionization parameter of about minus 1.5. That depends on the SED shape. And then the next one up, so this would be atomic plus 2, and this would be O plus 3 or O4. This reaches a peak ionization parameter at a of 100, a peak ionization parameter of 100, and we're even going to get even higher ionization. So this is in the theory that this ionization is a function of the ionization parameter, and the temperature also changes because the thermal equilibrium changes. But it gets tricky because the atomic coefficients also change. The recombination coefficient, that alpha in the ionization balance equation, can have a sharp dependence on temperature. So this becomes a multidimensional problem. You have to do a simultaneous solution of the temperature and the ionization all at the same time. To show you a slightly crazy idea, this really is the independent variable in this theory. The other graph shows one derived quantity, the temperature, and this shows the ionization. But we could make a plot showing the ionization as a function of temperature. For collision ionization equilibrium, the monotonic, as the gas gets hotter, it gets more ionized. But we've seen here that the temperature is complicated at low values. So what I did is I took a copy of this plot where we have ionization fraction versus ionization parameter, and then I made a new plot, but I swapped around the x-axis. This is now the temperature. The gas kinetic temperatures. This is the equilibrium temperature. So you can see that it's quite complex at temperatures below 10,000 degrees. There's nothing particularly monotonic. It's doing kind of a drunkard's walk back and forth over here. That's because there's more than one stable point at that phase of the ISM. And then when it gets going to pretty warm temperatures, it becomes monotonic and nicely sorted. So next time, let's talk about how to measure the ionization parameter with a telescope. So there's some well-established tricks that are used to do that. So I'll see you in the next video.